Hi, Maya. Well, we're gonna look at some more logistic equations. I posted a document on the website yesterday that hopefully might clear up some confusion. I don't know if anyone had a chance to take a look at that, but yeah, we're gonna take a look at we're gonna look at two separate equations that we can use to kind of attack these problems, and they're almost identical equations. They're just slightly different, and one sometimes works a little bit better than the other. So we're going to take a look at those, and then we'll look at some of the examples from that worksheet that I posted a couple days ago. And I'd also like to talk a little bit about the BC exam, because I watched an interesting YouTube video about it today, and I posted it. I don't know if anyone's had a chance to take a look at it. You just looked at it? Okay. And anyone else have a chance to take a look at it? No? Okay. Mm-hmm. Oh, right. Yeah, that's right. The derivative is going to be 1. Like once it hits 1, then that's the inflection point. Is that what you're saying? Oh, yeah. Okay. Oh, beautiful. So then whatever u equals 1, just so you can just solve that. Yeah. Yeah, and that's what you would get using just like the long version without doing the u sub. But that just simplifies it. That's cool. I like that. Yeah, so I want to just talk a little bit about these two formulas. So the one that we that I showed you is this one here. So it looks like y prime is equal to k times y, and then we had this little factor out here where we had 1 minus y over L. Right, that was the first version of the formula, and really the only version that we looked at. But I was looking through Mr. McIntosh's notes, and he pointed out that there's a different version of this that actually is really useful. So I thought I'd show it to you guys today, and I posted his notes on the website, so you can check those out if you have a chance. So the alternate version is to, well, I'll just sort of derive it. So it's basically the same as this one, except what we do is we're going to sort of like factor out an L. So basically what we're gonna do is we're gonna have well, we'll just multiply this by L over L. So I'm gonna just take a look at this. So k times y times 1 minus y over L. And we're going to multiply this by L over L. And when I do this, the numerator is going to distribute throughout here. So then we're going to have something like this. We'll have k times y times L minus y. And then we've got times 1 over L. And then what some people end up doing, so like this k right here is like, it's a constant, right? It's like basically like the rate of change, or not the rate of change, but the it's kind of like the exponent on our exponential function, right? It's a thing that is like relates to how fast something is increasing. It's like the proportion that we increase on a daily basis if we don't think about the like 1 minus y over L portion. But then so is this, like the limit portion is also a constant. So what often people will do is they'll sort of combine this k and this L together. So we can just have this written as k over L times y times L minus y. And you might actually see this where this is actually just one constant. So you might see this, and I'm going to just write it as sort of like a bold k, because it's a different k that looks kind of ugly, but you get the idea. So this is kind of like a bold k. So we could have this formula, and now this big K kind of has this L in it. So we might actually see some logistic equations that are or logistic differential equations that have this form to them, where we have some constant times y times L minus y, and that's a little bit easier to handle. And it really describes like a really similar thing, right? Like as y is like when y gets like is small, then this whole thing gets big. Also L minus y gets big. So I'll just write, maybe I'll just write arrows, like, so when y gets small, L minus y gets big, and then when y approaches L minus y gets small. So it has the same effect. It's just that it's not so much thinking about it in terms of like going from 0 to 1. It's going from something like small, like big to small. So so we're gonna sort of, like, with these questions that I posted the other day, this formula is going to be really handy, because it's going to sort of leave out some of the algebra that would normally cause us some trouble. So this one here, yeah. So this formula, so this is one of the constants in the formula. So when you end up solving this differential equation, and it doesn't matter which one, so if you solve this differential equation or this differential equation, you're going to get some constant out there. So you get basically this. So excuse me, I got the hiccups. So when you solve, like let's solve this first one, and I'm not going to go through the algebra. We already did it once, and it's kind of a pain in the butt, and it's really messy. But I think you get the idea that we'll get that y is equal to L over 1 plus a times e to the negative k times t. So that this a right here is a constant, and you can calculate it by taking the difference between the limit and your initial population and dividing it by the population. Sorry, are you talking about the difference between these two, or the difference between like this one and this one. Yeah. Okay, so the first one, okay, so if you're watching on YouTube, a student just asked, like, what's the difference between these two formulas? So we've got, and I'll just rewrite the one that's up here. So it's k times y times 1 minus y over L. What's the difference between these two formulas? Well, the one on the right, this is what we're starting with. This is our differential equation. So this is our differential equation. And this is the solution to the differential equation. Okay? So we're starting off with the green one. Let's call it the green one. So we're starting off with this one because we're sort of we're making a model of what population growth actually looks like. And a nice way of modeling it is just to look at the rate of change, right? So that's why we have this differential equation. This is a y prime, right? So we're talking about the rate of change. So the rate at which the population changes is, well, it's going to be proportional. Like this k right here is our proportion. The rate of change is going to be proportional to the population that we have, right? So the bigger the population, the faster our population will grow, and that k kind of just is sort of like an adjustment, right? Like if we were to solve this one, y prime is equal to k times y. Well, when we solve for this, you might remember that we got something that was like y is equal to a times e to the k times t, where t is the other variable that like it's time, right? So anytime you're talking about a rate, you have to have two variables sort of compared to each other. So this is like a good model of population growth, and this k right here, that's kind of like how exponential is it? Like you could, like, not all exponential functions grow very quickly, right? Like if k is extremely small, like if k is equal to 0.00000, right? If it's like there's like 1,000 zeros, then the exponential function actually does take a very long time to grow. And it eventually will grow very large, but it might take some time. So this k value is kind of like saying, okay, how fast are we growing exponentially? So that's what the k is. So, and that's sort of consistent with this model too, right? That y prime is equal to, well, some proportional, so that the rate of change is proportional to the actual population that we have. But then there's this portion here that's saying, okay, well, we have to be careful because populations do have some kind of hard limit, right? Like you can't have an infinite number of humans on a planet. So, like, what is the limit? And that's what L is. And the idea is that as y gets closer and closer and closer to L, this is going to get closer and closer and closer to 0. Whereas when it's the other way around, when y is very small, like if y is like 0 or 1 or 2, then this is very close to 1, right? Because you'd have something very close to 0, and you'd have 1 minus this kind of 0-ish thing, and then now you have this sort of exponential growth. But as y gets closer to L, this turns into 0. So this is kind of the beginning of our model, but as you can probably imagine, it's not super useful to only know the rate of change in a population. Sometimes you actually want to know what the population is, and this formula on the left tells you what the population is at any given time. So you have a few variables. When you solve the differential equation, you have a few variables. Some of them are constant, and you have one actual variable. So this L is the limit, right? That's I think that limit is kind of maybe a loaded word. So it's often also called the carrying capacity. right? Like that's the most we could possibly have, right? Like we can't have any more than L. And then A is just it's some constant. It's L minus your initial it's L minus your initial population divided by your initial population. And then K, here's that same proportion K, right? And then we have T over here, and T is time. So as time progresses, this number is going to change. So does that answer your question? Yeah, I suppose that y. I mean, that's what you're solving for, right? I mean, this is a function, right? So y, in this case, y is a function of t. So y is a function of t, okay? So, and y is describing some kind of population, right? So this is kind of like our population as a function of time, right? So yeah, I just want to go over a couple of the different formulas. So, pardon me? I'm going to break it down into 4 formulas that you should know, and you should be able to go back and forth between them. So let's start off with the one that we already, or the 2 that we supposedly already know. So those are going to be well, the ones that I already just wrote down. So these 2. So I'll write them down nice and cleanly. So I'll just write so formulas. We should know. And what I mean by that is memorize. Okay. So there's the first one. So y prime is equal to k times y times 1 minus y over L. And that goes hand in hand with this formula here, which is that y is equal to L over 1 minus a times e to the minus kt. And here, just on the side, we should know that a is equal to L minus y naught over y naught. Okay? And that's what a always is. This is just a constant. Good point. Yeah, thank you. 1 plus a. Thank you. Okay, so then the other 2 formulas are just variants of this initial one. So the other one is y prime is equal to k, and I'm going to sort of maybe make it a different color k, because it is a different k. So these are not the same. They're not the same k. Okay, so the other one is k times y times L minus y. So in this case, like this k is equal to the blue k divided by L. So, I mean, I suppose we could use a different letter, but the thing is that we're going to be seeing this k come up regardless, so we just need to be aware that these are different formulas. The k is just a constant, so in different contexts we're going to have a different k. So we just have to be aware that this green k kind of has an L taken out of it. So in this case, like when you see like, and you'll be able to notice the difference between these, because in this case we're going to have 1 minus something, or like 1 minus y over something, and this one is going to be some big number like our limit minus y. In which case you'll probably be able to notice that our k here is going to be quite small. I mean, usually k is very small. It's like most of the examples that we saw, k is like 0.01. But if you end up having to divide that small number by your limit, like L, then you're going to have like 0.0000001, right? So this k is going to be quite small. And again, this is like, we're all just kind of, like, we're still kind of stuck in the theory here. When we actually do a few examples, then I'm hoping that this makes a little more sense. But if you were to solve this differential equation, it looks a little bit different. We get that y is equal to L over 1 plus a times e to the negative L times k times t. And this is the green k, by the way. The green k. Which I'm hoping makes sense, because the green k, like this green k, is equal to the blue k times L. So these are the same, it's the same formula, right? It's just that one has a green k, the other one has a blue k, and the green k and the blue k are different by a factor of L. So that's really the only difference. The reason why is because sometimes you'll be given a differential equation in this form. In which case, instead of having to convert to this and then convert to this, you can just go straight to the actual equation. Yeah. So yeah, it's the same thing. It's kind of like if you know how to speak 3 languages, right? Like, so instead of, you know, like let's say that I know like French and German as well as English. Like, let's say I heard a French poem and I wanted to translate it into German. It would be nice if I could just go straight from French to German instead of having to convert to English first and then English to German. Do you know what I mean? Like you might be given a differential equation in this form, and then instead of having to go through all the trouble of, you know, solving the differential equation, which I'm hoping that we all agree is kind of challenging. Like it's not impossible, but it's a lot of work. So it'd be nice if we could just use our formulas, and if we can just go straight from here to there, then that's what we want to do, right? Instead of having to, you know, be like, okay, well, I got to convert this k into the other version of k. It's just that if you get, sorry, go on. Yeah. So yeah, I mean, and that's exactly what you can do, right? Is that you can just say, okay, well, here's my limit here. I'm going to just multiply this by L over L, right? And then the bottom L would be distributed, and then you'd have 1 minus y over L, and then the big L would kind of turn this green k into the blue k, right? That's really all you'd be doing. Okay, do we want to do some examples now, or do we have any more questions about this stuff? Okay. Yeah, absolutely. Yep. Yep. Well, you can assume that, yeah, like right now, I would consider it to be times 0. Like in this moment is times 0. So if they give you the current population, you can think of that as the initial population. Does that make sense? Oh yeah, absolutely. Yeah. Yeah, so just if you didn't hear that, like if you're watching on YouTube or whatever, the question is, so if they give you the current population, is that the same thing as the initial population? The answer is yes. Yes. So y naught can be interpreted as initial population or current population. And I mean, I'm sure that there's some situations where what I just wrote down is false. Like you could be given a question that says like, oh, 10 years ago the population was this. What is the population right now? Well, in that case, you kind of have to interpret it in your own way, right? So the idea is that like if you were given the population 10 years ago, well then yeah, that would be your initial population. That's what you'd start off with, and then you'd be solving for like t equals 10 or something, right? So we do have to sort of interpret these problems kind of as they come. But in that question, I think for question 6, I'm not sure if I quite finished question 7 myself. Yeah, so for question 7, they give you the current population as well. So in both of these questions, why not is going to be the current population. Does that answer your question? Exactly. Yeah, the t changes accordingly. Yeah, absolutely. Okay, so let's do a couple questions. I'd like, so the questions that I really want you to sort of struggle with on your own if you haven't finished them is questions 1 through 4. So the first 3 questions are really about these different formulas and how to interpret them. And like I don't want to just do them for you because it's important for you to struggle with this on your own. And there's solutions on the website as well. And I also posted that document, and I'd recommend that you take a quick peek at that document. I'll show you what I was talking about. So APCalc, there we go. Yeah, notes on logistic functions. So this is it here. So it's a great document. I'd highly recommend going over it. It's very thorough notes. And my only regret is that I didn't show this to you earlier. Because it's a great document. So take a look at this. So yeah, Mr. McIntosh sort of talks about the different versions of these formulas. So apparently he prefers working with the other version, but I mean, again, it's the same formula, so it doesn't really matter which one you prefer working with. What matters is that they're the same, but you should be able to go back and forth between the 2 different versions. And then he's got a great blurb about how these all work. And then I think that here he's using the letter C. We've been using A. It's all the same thing. Yeah. Okay, so let's do a couple questions then. Which one do we want to do? So I guess we'll do question 5 together. So logistic questions. Question 5. Okay, so we've got the rate of change with the population is given by y prime is equal to 0.0005 y. Yada yada yada. I'll just write it down. So this is number 5. Okay, so I've got this differential equation here. So it's y prime is equal to 0.000. That's 3 zeros and a 5 times y times 1500 minus y. And that's it. And then it has an initial population of 40. So y naught is equal to 40. So then we'll just kind of go through each one of these questions. So question A is, what's the carrying capacity? Carrying capacity. Well, that's just what L is. So let's just talk about which version of the formula this one is written in. Well, if we go back a little bit, so it's either going to be this one because it's a differential equation. So it's either going to be this one or it's going to be this one. And I see some big number minus y. So I'm guessing it's, well, I'm not actually guessing. I know it's this one here. So so that's the one with the limit or the L. sort of underneath the k, right? So like I said before, see how small this number is? This is a teeny tiny number. Well, it's because we've gone ahead and divided it by L. So we've divided this by 1500. So let's actually write out all these variables. So so this one is going to be our k, and that's like our, I guess we used a green k before, or maybe it was blue. I don't remember which color it was, but it's that smaller k. This is going to be L, and that's pretty much all we have. So the carrying capacity is going to be L. So that's part A. Part B is what's the A value? So the A value in the formula for P of T. And P of T is just what we've been calling Y, right? So P of T is you know, like the population as a function of time. So we don't have much to do here. So except just fill out the formula. A is equal to L minus Y prime, or sorry, not Y prime, Y naught over Y naught. And that's equal to, well, L is 1500 minus 40 over 40. And, well, that's going to be, what, 1460 over 40. And I did this already ahead of time. I can't tell you how annoying it is not to have a calculator. I think I need to go back to school and pick up my calculator. I mean, I guess I could punch it into my computer. What is it? 36.5. 36. Pardon me? No, I forgot it at work or at school. It's in my desk. But I mean, like, I have a phone that has a calculator in it and stuff. But like a lot of the stuff that we've been doing is like stuff with logarithms and the Euler's constant and stuff. Like, that's the stuff that we usually need a calculator for, and it's a pain in the butt to use an iPhone calculator and all that stuff. So I've been using like Wolfram Alpha a lot for that, and Google actually has a fairly robust calculator, so I've been using those. Anyways, so that's what A is equal to. So now we can punch this into the actual solved equation. So remember, when we have this form of the equation, where we've got this sort of smaller version of k, our solved solution is going to be a little bit different. It's going to be, well, I'll just write out what it is in terms of the variables. It's still going to be L over 1 plus A times E to the minus K times L times T. So the only difference is that we just have to make sure that we have this L in the exponent of E over here. So when I do that, well, my limit is 1500. So I've got 1500 over, and then 1 is 1. A is 36.5, 36.5. Then we have E to the minus. K is 0.05, 0.0005 times 1500 times T. And we just have to simplify that. And because I don't want to have to search around for a calculator, I'm just going to copy my answer that I had earlier, which is, yeah, 3/4. I think it's 0.75, or negative 0.75. Yeah. So I've got 1 plus 36.5 times E to the negative 0.75 T, or if you like, 3/4. Okay, so that's that one. So there's our formula for the population. So let's just take a second to interpret this. So what this equation is saying is that if we want to know what the rate of change of a population is, what we're going to do is we're going to take the current population and multiply it by 0.0005. So at any given time, you can multiply the current population by this, and that's what the rate of change is going to be. However, we're also going to multiply that by the limit of the population, provided that y is small. And if y is close to that limit, then we're going to multiply this by 0. So as y approaches the 1500, so like when y is, say, like 1400, well, there's not very much room for other people to, be born. So the rate of change is going to be close to 0. We're going to kind of peter off and sort of have like the same amount of population every day. And if we end up graphing that, then, or I guess I should say solving that. So if we ever want to find the current population, this is the formula for that. So that's what's so useful is that you can take a very simple model, which is just talking about the rate of change, and then end up getting an explicit model that tells you exactly what the population will be at any given time. Okay, so for part D, it's asking for the other form of the equation for y prime. So what that is saying is that, okay, so we have these two forms of the equation. We've got this one and this one. We should be able to go back and forth between the two, and it's asking us to do exactly that. So what we're going to do is we're just going to multiply both sides, we're going to multiply this side by L over L, and that should give us exactly what we want. What did I do here? Here we are. So the original one was y prime equals 0.0005 times y, times y times 1500 minus y. Okay, so we're going to multiply this by 1500 over 1500. Okay, and then I'll just color code these so we know which is going where. So this pink one I'm going to multiply over here, and let's call this one green. So this green one is going to be distributed inside these brackets, and I'm left with, pardon me? Yeah. That's exactly what it's asking for. I'm just kind of doing it with like just very explicit algebra. So we can do it both ways if you want. What I'm doing here is, well, y prime is equal to, well, 1500 times 0.0005 is 0.75. And 1500 over 1500 is 1. And I've got y over 1500. So yeah, that's pretty much all I did, is that this was one version of the k, this is another version of the k. To go from the small k to the big K, you just multiply it by the limit, and then you write the limit as a denominator under y, and you do 1 minus that instead of the limit minus y. So yeah, I mean, you could go directly there. I prefer to do things just by writing out the algebra, so I have some kind of record of what I did, and it kind of explains my thinking. But if you want to go directly there, like if you want to just say, okay, well, all I have to do is just multiply this k by L, and then I'll get some bigger number, and then over here I'll change what's inside the brackets to sort of fit whatever the equation wants. That's fine too, but I just think that there's more room for error if you don't actually show your work, right? And then sketching P of T. So to be frank, I don't really want to do that. So I'll just use Desmos. So let me just connect my keyboard. Okay, so what do we have here? I'm going to do this. Oops. How do I do that? And this one is what I want. Look at that. Okay, so we are going to graph. Well, let's actually graph both of them just so we can see what we have going on. So I've got 1500, or I'll say y is equal to 1500 over 1 plus 36.5 times e to the power of negative 0.005. 0.75 t, or I guess, yeah, we can use t, why not? So that's weird. Oh, no, it's not weird. I was going to say it looks like there's no limit to it, but then I was like, wait, what would the limit be? Well, it's 1500, right? Obviously it's 1500. So here it is. Yeah, how do you do that again? Ah, like this. And why don't I squish the x-axis down? Hey, look at that. Too bad we couldn't get a logarithmic scale. I'm sure you can. Does anyone know how to do that on Desmos? Settings? Cool. Like these settings? No. These settings. Okay, x-axis, y-axis, step, radians, degrees, grid, reverse contrast, projector mode. Oh, oh, that's nice. I like projector mode. Yeah. Oh, I think that just undid. Anyway, we don't have to have a logarithmic scale. But yeah, you can kind of see what's going on here. So our asymptote here, so we've got two horizontal asymptotes. I'll graph them both. One is y equals 0, and the other one is y equals 1500. So there you have it. So we got awfully close to 1500, but we don't actually approach it. And then also, you can never have a population of negative anything, right? So it doesn't make sense to talk about a negative population. And then there is our there's our initial population of 40, right? So that's all consistent with the information that we were given. So yeah, I think that's pretty cool. And while we're here, let's graph the derivative. Let's do this one, and maybe you'll see why the first one is actually a little bit nicer. It's actually this first one, like I'm talking about this one here. This one is much easier to type into a computer because you don't have a denominator, and denominators are kind of annoying when you're typing stuff out onto a computer. So let's graph y equals, oops, there we go. Y equals 0.75 y times 1 minus y. Oh no, I was going to do the first one. Sorry. 0.0005 y times 1500 minus y. And right. Okay. Oh, I see. So make this f of t. Do you want me to get rid of the asymptotes? Is that what you're saying? Yeah. Oh, here, let me get rid of this. Oh, I see, I see. Ah, there it is. And oh, why don't I just use x here? There we go. Right? Yeah, okay. So, so yeah, really all I wanted to do was just write what the derivative looks like. So you can see right here we've got a maximum, and it's looking like it's right around. Well, I should learn how to use Desmos a little bit better. It's right around sort of the. I mean, you can see exactly where it is. It's right around this where x is equal to 5. So it's right around 4.796. So yeah, hopefully that didn't hurt your brain too much. And we'll do this. How do I make this full screen? Oh, brother. There we go. Aha. Okay, should we do another example then? Yeah. Okay. I'll take a minute just to talk a little bit about the AP exam. So I watched this video today. I recommend that you watch it too. And I posted it right in the Discord. I guess I'll put a link in the YouTube description, but I don't actually know if anyone's watching YouTube videos, so I'll take that with a grain of salt. By the way, today YouTube totally died on me. It was awful. In my grade 10 advanced class, right in the middle of it, the live stream just cut right out, and I wasn't able to connect again for like 45 minutes. So I'm a little hesitant about using YouTube going forward, but we'll see. Well, I told everyone to go into Discord, but yeah, I don't have the whole class on Discord yet. So yeah. Anyway, so the College Board released which topics they're going to remove from the AP exam. So I think it's important that you guys know that, and I am going to like my instruction is going to reflect that. And I mean, it does kind of, it hurts my soul a little bit to just be like, it's not on the exam, so we're not going to learn it. But just given the circumstances, I really think that we do need a bit of a relief, because we still have a lot of topics to cover, and I, for one, am finding it challenging to teach the topics in this sort of digital format. I mean, I think that we're doing a great job as it is, but I think that it is also just a little bit harder to learn a topic when you're kind of stuck inside your house all day and yada yada yada. So basically, the TLDR of this is we're going to skip the last chapter because we aren't going to be tested on the very last chapter. So chapter 12, which is on parametric equations and polar coordinates, I hate to say it, we're not going to do them. Maybe like after the AP exam, like if we want, we could do a bit of an investigation into them. I think that it's like a really interesting chapter. It's like a very heavily applied area of calculus. I mean, all of calculus is heavily applied, but polar coordinates are really interesting because you can actually start to have functions that actually kind of like look like this. Like this is a function, even though like it doesn't pass the vertical line test or anything like that. So yeah, you can have these really cool functions that are kind of like different circles. You can have a function that's like a spiral, like this. Is really, really cool stuff, and it was one of my favorite topics in calculus. So it's kind of a shame that I'm just going to cut it out, but I think that just in the interest of time, I think it really makes the most sense. And so that's what I think they are calling what is it? I think they're calling that chapter 10, or section 10 or something like that. No, sorry. Unit 9 is what they call it. So they're calling that Unit 9. So there's no Unit 9. And Unit 10, which is our chapter 11. I think it's Unit 10. Let me just double check here. Yeah, Unit 10, which is on like sequences and series and stuff. So we call them Taylor polynomials and series in our book. There's a few topics that have been omitted from the exam, but I think it's just best if we just kind of do the whole chapter rather than try to like pick out certain odd things that aren't going to be included in it. So basically what I'm trying to say is that after this chapter that we've been working on for the past couple of weeks, we only have one chapter left because we're going to skip chapter 12. So I just wanted to make that clear. Yep. Mm-hmm. Yep. Totally. Well, we could do that. I was kind of thinking about doing sort of maybe just like an independent study. So I mean, and if you wanted to collaborate, you could do that online. I think that we've all been very creative and very flexible so far when it comes to learning and communicating. So I think that we could still do like a partnership, but then at the same time I would want to be especially flexible for those who just don't feel comfortable doing something in a group or in a partnership or anything like that, just due to the situation that we're in. So I think that I still would like to do an independent study. So basically, I could help you find a topic that you're interested in, or you could find your own topic, but it would have to be a math topic. And then you would just do a research project and then submit that to me. If we can talk more about what that will actually look like after the exam. My guess is that it would probably look like you giving me some kind of document, and then I would give you some feedback, and then as you're writing the document, I would sort of help you find some sources and things like that. But if we wanted to do something a little bit different, like if you wanted to go live on Discord and we could all watch you kind of talk about your thing, that would be cool too. I think that the important thing is that we just have to be really flexible and kind of open to change. And even if we do decide to do something, I think that it's important to know that plan might change. But I think that we already know that. I think that just everything that we have been doing has just been changing every single day. So yeah. And if you have any suggestions about what you'd like to do for the project afterwards, definitely let me know. I'm certainly open to suggestions. And if we all decide that like maybe we just want to do chapter 12, then we could do chapter 12. And how I would assess you, I don't know, we could talk about that. Maybe we could just do a regular old test, or maybe I could get you guys to kind of make your own study guide or something like that, or like a little encyclopedia of polar coordinates and parametric equations, something like that, So at this point, I'm very much open to different suggestions and ideas, but like I said, we have to be flexible because things are definitely gonna. Well, I shouldn't say they're definitely gonna change, but they probably will change. So no matter what we decide, there's probably going to be some kind of wrench being thrown into our cogs. So, Okay, cool. Are there any other questions before we sign out here? Because I've got to start preparing for my grade 11 class. It starts in about 5 minutes. No, you're good. Yeah. So yeah, I guess what I'll do is I'll post some stuff on my website about the assignment, and I'll get you to sign into CrowdMark, and I guess what I'll do is I'll give you a well, maybe we can talk about that right now then. So, well, it's not going to be timed in that, like, I'm going to time you from the moment you open up the document to the moment that you submit it to me, but I am going to have, like, a deadline. So, in a sense, there is a time limit between the time that I post it and the time that there's it's due. How are you guys, like how are you doing in terms of like your workload? Like, are you guys like completely swamped, or are you bored and have a lot of time on your hands? Like, how are you guys holding up? Destroyed. Mm-hmm. Okay, so what about due dates? Like, do you guys have any big due dates coming up? Okay, so if you're watching on YouTube, the general consensus is that people are okay, but we're kind of at capacity. We're approaching L. Like, if we were to like go back to Desmos, like we're probably like what, right around, like, I guess you guys can't see my pen, but like you're approaching the asymptote. So we're approaching the carrying capacity of workload. So I mean, I'd really would like to just not give you any work over March break. So I'm hesitant to say like, oh yeah, you can hand in the assignment like on Monday, but then what that's gonna look like is, okay, well, I'll take the week off and then like I'll worry about it all of March break, and then kind of like procrastinate and then leave it to Sunday. So maybe what we can do? Do you guys have anything due? Like, do you have any assignments to do over March break? Okay. Yeah, that's kind of what I'm thinking. Is maybe have a due date of Monday, and then you can do the weekend, and then we could kind of just consider this Saturday and Sunday coming up as like it's not March break yet, and then because I really want to just give you a break, because you guys really need a break in some things. So maybe what we'll do is we'll have that the due date is due at like 8 a.m. on Monday. So you would have the weekend to do it, but then March break, like you'd have an actual break. No, don't do that. That's the whole point. I it's gonna be like the same amount as a test. I'm basically gonna give you the test as an assignment. So, if you really just like took all your distractions away, it would probably take you about 2 hours, because that's about the time that it takes for us to do the test. So, I'd prefer not, but I mean, like, there's really no way that I can prevent you from doing that. So if you're gonna collaborate, I mean, why don't we say this? If you're gonna collaborate, then tell me. So like, and I won't take any marks off, but it's just useful for me to know if you like worked with someone else. So what we'll do is we'll say, so collaboration we'll keep to a minimum, but it's not disallowed. But if you do collaborate, you have to tell me. So there's obviously some honor system in there, but I think that we don't really have anything to lose by, like, if it, yeah. Mm-hmm. Yeah, I know. Yeah, your mark definitely means a lot to you, and you know, whatever grade you get is going to be like reflected on your report card and everything. But at the same time, like, the whole purpose we're here is to learn, right? And you know, I kind of get the sense that most, if not all of you, want to go to university next year, and okay. Did is that Crystal here? Do you have a question? Okay, go ahead. Pardon me? Tomorrow. I'll be posting it tomorrow. Yeah. Yeah, I know. I can see a few people coming on in. So yeah, I'm gonna go. If you have any questions about the assignment or anything at all, don't hesitate to ask. But I'll post it tomorrow. So you can either post your questions in Discord or Instagram or an email, whatever you like. But I'm gonna sign out because yeah, okay. Are the midterm report cards going to be delayed? I don't think so. I know that the middle school report cards are being handed out tomorrow, so they weren't delayed at all, and they're like right in the middle of this. So I assume that our report cards are going to be just like regular report card time, which I think is in about a month from now. So yeah, I mean, you guys are doing great. I don't know what you're so worried about. You guys are all like doing super well. So yeah. Anyway, I'm gonna go, and actually I don't think I am gonna go, but because I'm gonna be online. But yeah, you guys should go. So bye bye. Unless you're in grade 11. If you're in grade 11, stick around. Okay. Oops. Hey, grade 11ers. Okay, we'll get started in just a second. I'm just going to make a new YouTube stream.